So my talk here is the title. So it's on the middle between theoretical physics and mathematics. And I want to introduce this exciting direction. So first, several words of introduction. The role of topology in the theory of condensed matter first became clear in the study of the quantum Hall effect, starting from the papers by Laughlin and Towles with co-authors. From the physical point of view, the topological invariance is equivalent to adiabatic stability. A key role in the classification of topological objects in the theory of solid states is played by the study of their symmetry groups. The description of possible symmetry types goes back to physicist Kitaev, who proposed a classification of topological insulators based on the investigation of their symmetry groups and their representations.
Excuse me.
Yes?
What are insulators?
What?
Insulators.
Insulators in Russian это диэлектрики. Topологические диэлектрики. So in our talk, we pay main attention to the topological insulators invariant under time reversion. Such systems are characterized by having the wide energy gap, which is stable under small deformations. And this is the idea to use topology for the study. An example of these systems is provided by the famous quantum spin Hall insulator, which has a non-trivial topological Z2 invariant, which was introduced by Kane and Mill. And now let me switch to my talk in detail. And I start with the classical Bloch theory. This theory, maybe I should stand here, maybe it's better. The classical Bloch theory describes the properties of solid bodies which have the crystal lattice, called the Bravais lattice. From a mathematical point of view, this lattice is just a discrete abelian group gamma in the space Rd of 3 dimensions, which is isomorphic to Zd and acting on Rd by translations generated by vectors from our lattice. The behavior of free electrons in a solid body is governed by the so-called one-particle Schrödinger equation. It has the following form. This is Laplacian, and here is the potential which is invariant under the action of gamma. Such operator commutes with all operators T gamma of this translation operators. Let us denote by gamma prime the dual lattice. This is lattice in the momentum space, like physicists would say, but this is just a dual space to our Rd, which is defined in the following way. Gamma prime consists of the vectors from this dual space, such that their values on gamma, for all gamma from our lattice, are integers up to this 2 pi. So this is a definition of gamma prime, and the fundamental domain of this lattice gamma prime, or as physicists would say, the unit cell, is called the brilliant zone, and this is one of the most important notions. I will call it, I will write it like that. The functions which are invariant under these translations may be considered as functions on the torus, which is Rd modulo gamma. Let us denote by H sub 0 the Hilbert space of L2 functions on this torus, which is the same as that, with respect to the measure on Rd modulo gamma induced by the Lebesgue measure dx on Rd. Very good example, this is exponentials. I denoted by ek, which is e into the power ik times x. This is the inner product. And this exponential belongs to h sub 0, to this h sub 0, if k is from dual lattice. Moreover, such functions form an orthonormal basis in h sub 0. The next very important notions are what is called Bloch functions. These are functions, smooth functions of the following type. Here we have again this exponential and phi of x, where phi of x is a C infinity smooth function with invariant under gamma. So we may consider it as a function from C infinity on this torus. The space of all Bloch functions with quasi-momentum, this K is called quasi-momentum. This is important notion. The space of all Bloch functions with quasi-momentum K is denoted by LK. If you apply the Schrödinger operator to such block functions, we will get the following. Again, this exponential, and this is some Hamiltonian, some operator here. H sub k is called the block Hamiltonian. And it has the following form. Here is vector gradient plus k. This is a scalar product, phi plus y phi. This hk, which is one of the main notions, as I said, maps the space of smooth functions on the torus to itself. In particular, it follows from this formula that the original Schrödinger operator H maps the space of block functions to itself. So this block functions is a very important notion, and in fact they also, in some sense, they form a complete system, but one should be careful. So I will not give the precise notion. If we denote now by ik the operator of multiplication by this exponential in L2, then we can rewrite the above formula, this formula. We can rewrite as follows. This is just conjugation, and the conjugation with respect to this ik is this block Hamiltonian hk. Now we consider this Hamiltonian hk on the space of smooth functions, and denote by h of k the closure of this operator is this L2 space. In fact, its definition domain is easy to write down. It consists of the following Fourier series, such that this thing is this series converge. It has a discrete spectrum, and its eigenfunctions phi m of k are solutions of this equation: h of k, phi m of k, e m k, phi m of k. I note that this is an equation for functions on x. So the functions phi m of k are the functions of x, but they depend on two parameters, which is not usual. This is discrete parameter m, which is just natural number, and continuous parameter k here, which is a vector from this brilliant zone, from this torus. And for every fixed k, if we fix k, and here we have only m, they form a complete orthogonal system in the Hilbert space H2. Consider now the physical interpretation of this mathematical picture. I will assume so-called type-binding approximation. I will not explain what does it mean. But in such approximation, we can assume that there is only a finite number n of active one-electron levels, corresponding to the eigenfunctions Em of k. The collection of all energy levels corresponding to the functions Em of k with fixed m is fixed, but k is a vector from the brilliant zone. This is called energy zone. In this way, the functions Em of k determine the zone structure of a solid body. And this is the main physical notion in this theory. What is the basic state of a system of n Bloch electrons? Basic means that this with minimal energy. It has the following structure. There is a number of completely occupied one electrons levels with energy which does not exceed the quantity EF, which is called the Fermi energy. And above this energy, we have only non-occupied or empty levels above it. And the interval of energies between the highest occupied level and the lowest empty level is called the energy gap or forbidden zone. The solid bodies with wide energy gap are called insulators. So this is the definition of dielectrics, if we use Russian word. The Bloch functions. Now we take this eigenfunctions and consider the corresponding functions, Bloch function, psi m of k. They are the eigenfunctions of original Schrödinger operator H, and in some sets, which should be made clear, they form the complete orthogonal system. Let us denote by H sub k the compression of the space Lk. This is a space of Bloch functions with fixed k, with respect to the norm, which is determined by isomorphism between H sub 0 and H sub k, so that this Ik, this multiplication by exponential, extends to isometry between H sub 0 and H sub k. And now we can construct the vector bundle over the brilliant zone, which I denote by this Gothic H, having the fiber HK, this HK, over the point K from brilliant zone. And denote by calligraphic H the Hilbert space of square integrable sections of this bundle with inner product like that, where here is the inner product in HK, which is a Hilbert space. So this is the starting point. It's of course well known classical block theory. And now something new, maybe in the middle of the last part of the last century. Let us speak about the topological invariants. What are the invariants which we can use? Consider again the block Hamiltonian, which I now denote by H sub 0 K, which describe a zone insulator with forbidden zone on the level of Fermi energy EF. I will always assume that EF is equal to 0. We can diagonalize this block Hamiltonian by taking the conjugation with some unitary matrix depending on K. So we will get the diagonal matrix with this eigenvalues here. I suppose that first P levels, which lie above the Fermi energy, are empty, and the occupied levels correspond to the energies below the Fermi energy. So what can we do? Now we consider what physicists will say adiabatic deformation of this Hamiltonian. Mathematically, this means that we consider continuous deformation of our Hamiltonian in the class of considered Hamiltonians, which not affect the forbidden zone. We cannot touch it. And one can find such deformation which transforms H sub 0 into the Hamiltonian, which I denote by H sub 1, or signum of H0, which has only two eigenvalues, equal to plasma or minus 1. It's very easy to prove that this is possible if you use the spectral theory for the Hamiltonian. In other words, we can find a continuous map U1 from brilliant zone to the unitary group, such that this conjugation gives us a block diagonal matrix where in one block there is unit matrix, and in another block this is minus 1. Note that the matrix U1 K here in this equation is defined only up to transformation of the following way. We can multiply U1 of K by this diagonal matrix, block diagonal matrix, where here is unitary matrix and here is unitary matrix. Then it's clear that this will not change. So we should somehow get rid of this ambiguity. Hence, the matrix U1 of K yielding a solution of the above equation determines the map from the brilliant zone, which is the torus, d-dimensional torus, to the Grassmannian, which is unitary group modulo this block diagonal matrices. So we have arrived at the problem of description of homotopy classes of maps from the torus, d-dimensional torus to Grassmannian. The general problem of description such spaces, which were called torus homotopy groups, of topological spaces X, was studied by Fox. That was one of the founders of the knot theory. It follows from his results that the homotopy classes, which I want to consider, are classified by D elements from the fundamental group P1 of X, D minus 1 divided by 2 elements from P2, and so on, this binomial coefficient CJD elements from pi G of X. This is, unfortunately, I have no time to explain why it is so. But let us explain this, apply this theorem to the Grassmannian. So now X is Grassmannian. Then we obtain for D equals 1, so when dimension is equal 1 of the torus, we have that the mappings of the circle to Grassmannian, this is the same as fundamental group of Grassmannian is equal to 0. For D equals 2, the homotopy classes of the maps from two-dimensional torus to Grassmannian are characterized by a unique invariant, since P2 of Grassmannian is equal to the integers. And for D equals 3, the homotopy classes of mappings from three-dimensional torus to Grassmannian are classified by 3 elements from the group P2, which is just integers, since P1 and P3 of Grassmannian are equals to 0. In fact, it's easy to describe what does it mean, what are the non-trivial classes in dimension 2 and 3 in the following way. This space of homotopy classes of mappings from t-dimensional torus to Grassmannian may be considered as classifying map for the bundles over TD. In dimension D equals 2, there is only one non-trivial bundle over T2, which is analog of the Hopf bundle. This is a bundle of S3 over S2. From the physical point of view, this case corresponds, as I said, to the one of most famous topological insulators, quantum spin-Wald state. In dimension d equals 3, there are 3 bundles over T3, which are pullbacks of the Hopf bundle over T2 with respect to 3 different projections from T3 to T2. So this is an explanation how they look like. Now we come to the question of symmetry. And I start with the most, for us, most interesting time reversal symmetry. What is the symmetry? This symmetry is given by the T transform. What is that? This is operator T, which satisfies the following condition. T squared is minus identity, and is anti-unitary in the following sense. T phi, T psi equals not phi psi like in unitary, but psi phi. For any states psi, phi, and psi. It implies in particular, it's very easy to prove, that the state phi and its T partner, T phi, are orthogonal to each other. So we have the following. Since the states have the same energy, it means that any energy eigenstate is double degenerated. This is effect, famous effect is called Kramer's degeneration. So all eigenstates are double degenerated. That's a non-trivial property. The symmetry with respect to T transform for the effect of Hamiltonian, this H of K Bloch Hamiltonian, means the following. So if we take the conjugation with respect to T, here we get H minus chi. So this is chi replaced by minus chi. Now, what is the mathematical meaning of all that? Mathematical meaning is given by the notion of involutive spaces. The topological insulators with time reversal symmetry are described mathematically in terms of involutive spaces. Definition. Involutive space X tau is a topological space X provided with involution. That is a homomorphism tau of this X with square equal to identity. This is involution. Such space will be called the R space. Here is an example of R space. Looking a little bit like a complex space, but this is not complex space. This is RPQ is RQ plus I RP. I involution is acting in the following. XY is going to X minus 1, my Y. And in fact, this T symmetry in the involutive space is usually given by reversion of signs of local coordinates. That's the usual thing. For example, if the sphere SD is realized in the space RD plus 1 in such way, then the T symmetry on it is given by the map X sub 0 is not changed, and all others are multiplied by minus 1. For the torus, which is the product of circles, with coordinate e to the power I theta 1, e to the power I theta d, this is just the change of the sign of these thetas. Very important notion, the set of fixed points of involution, tau. It is defined like that. So these are points which are fixed by tau. We call them fixed points. We suppose that this set consists of a finite number of points. In the above example of the sphere, the involution has just 2 fixed points, plus minus 1, and all others are 0. While the involution on torus, TD, has 2 in power d fixed points, which are given by these collections of epsilons, where each epsilon is plus minus 1. One more definition. The quaternion vector bundle, or Q bundle, I will call it Q bundle, E rho over the involutive space X tau. What is that? This is a complex vector bundle E over X, which provided with anti-involution rho, which is compatible with tau. Here, anti-involution rho is given by antilinear bundle isomorphism of E such that rho squared is equal minus identity. It is compatible with tau in the usual sense. If we project the action of the rho, then we get the action of pi. At fixed points X, the map, it will be a map in the bundle, in the fiber of the bundle, is an antilinear map with rho squared of X equal minus identity. So rho X, in fact, defines the quaternion structure, action of quaternions on the fibers. That's why it's called quaternion vector bundle. If we replace in this definition the anti-involution by the involution sigma, such that sigma squared is equal not minus identity like here, but identity, Then we obtain the definition of R bundle, E sigma over X tau. Now let us return to where we started, to the Hilbert bundle of the topological insulator. So I recall that this is a bundle over Brillouin zone, BRT. Fiber over X is the Hilbert space HX, and we denote by H the Hilbert space of its square integrable sections. Such sections are identified with physical states with eigenvalues E of X. So the time reversal transform on the space H, so on the space of sections of this bundle H, is given by the operator theta, which is an anti-unitary operator satisfying the condition theta squared is -1, and theta star is minus theta, so it's anti-symmetric. The Hilbert bundle provided with the operator theta becomes the Q bundle of this H, theta over X tau. So we can say that we had this tau, this involution on X, and we just pulled it back to H to get the anti-involution. The Hamiltonian H of X invariant under time reversal should satisfy this condition. This I just rewritten the definition. If phi is an eigenstate of H, so the H phi is equal to E phi, then theta phi is an eigenstate of theta H theta star with the same energy E, because we have this relation. So this is the same. The energy is the same. This eigenvalue. In other words, the states phi and theta phi, which belong to the same zone with the energy E of X, and each zone under this T symmetry is double degenerated. So this pair phi theta phi form the Kramer's pair. I said that this is most important notion in this theory. In this case, the rank of the Hilbert bundle should be even. That is equal to 2n, where n is a natural number. If T is the only symmetry of H, then each zone is precisely double degenerated. So H is represented as a direct sum of subbundles of rank 2. And in fact, everything, all considerations will reduce to the rank 2 case. So bundles of rank 2. So suppose we have this rank 2 bundle, and denote by Wi the transition function of the bundle Hi from X to U2. The T transform on H changes Wi to Wi times times complex conjugation. In terms of local coordinate, the operator theta capital X by this formula. It's very easy to deduce that WE transpose matrix of T of X equal to minus Wi of X. In particular, at fixed points, what is important? At fixed points, this matrix is Q-symmetric. Now, let me say a few, when I should finish.
5 minutes.
In 5 minutes? Okay. Then let me say a few words about very important notion in physics. This is Majorana states. Let H of X be Bloch Hamiltonian on the momentum space X. Again, we consider the case where this bundle is rank 2. Then the power of sections, Kramer's section phi and theta phi with the same energy may be considered as a quasi-particle composed of phi and theta phi. Its effective Hamiltonian is equal to H tilde of X, written in this form. It is T invariant, and the equation for an eigenvector phi of phi with eigenvalue E takes, in terms of H tilde, the following matrix form, which I just written down. Suppose now that on the space H, it is given a real structure I, satisfying the condition that I squared is equal identity and I star equal to I. A state psi is called Majorana state with respect to this real structure if it satisfies the reality condition. Having the time reversal operator, it's easy to construct this real structure, which acts on the Kramer's pair by the following formula. So you see that this pair is stable under this. So this is a Majorana state. So this is a quasi-particle is Majorana state. We can localize this definition as called by Majorana zero mode, the Majorana state phi sub 0, defined in a small neighborhood of a fixed point, such that at this point phi is 0, theta phi is 0, and the sign is changing at this point. Now I come to analytical topological invariant Z2 index. Suppose that the operator H had also H tilde is Fredholm. The operator H of x near the fixed point x sub 0 is the sum of the Dirac operator and quadratic error term, which does not influence the homotopy class. So the index of topological insulator is determined by the indices of Dirac operators at fixed points. In the neighborhood of fixed point, the operator H tilde may be approximated, as I said, by the Dirac operator, which in matrix form has this form. So the operator H tilde in the neighborhood of a fixed point is equal to the sum of the skew-symmetric operator D plus a quadratic error term, which does not affect the index. So for real skew-symmetric elliptic operators, Atiyah and Ziegler define their analytical Z2 index as dimension of the kernel of this operator modulo 2. So it is natural to define the Z2 invariant of topological insulator mu as the following sum: the sum of local indices in the fixed points equal to that. The physical meaning of Z2 invariant is that it coincides with the parity of the number of Majorana zero modes. Now, topological Z2 index. We shall describe the construction of topological Z2 index for the three-dimensional involutive spaces X. Suppose again that the bundle has rank 2, so the gauge group coincides with this unitary group U2. The anti-involution on the Hilbert bundle is compatible, this is Hilbert bundle, is compatible with the natural involution theta on U2. This is the natural involution of the unitary group. In other words, this W yields an equivariant map from our involutive space to this group U2 provided with this involution. If we have a smooth map from X to a unitary group of odd-dimensional space XD, in our case D equals to 3, then there is the following odd Chern character, which is given by this formula. What is important, what is written here, this is in fact corresponding to chain-while theory. So we take this matrix G minus 1, Dj, then in power 2k plus 1, and take the trace, and then the sum. Using this formula in three-dimensional case, we introduce the topological index like that. This is just integral of one of the terms from this Chern 3. So it is equal, precisely it's equal to that. Due to the T-symmetry, this topological index of the transition function W is defined modulo Z2. The assertion that the topological Z2 index for three-dimensional topological insulators coincides with the above analytical index, that is mu equal to topological index of W, may be considered as an analog of Atiyah-Zinger index theorem in our situation. So I can stop immediately.
1 or 2 minutes.
Okay, then I just very shortly recall what is K-Mill invariant. That was the first topological invariant constructed by physicists. This is a K-Mill invariant is given by this formula. We take the product over all fixed points of Pfaffian of Wx divided by square root of determinant. Recall that at fixed point x, the transition function Wx is a skew-symmetric matrix. So the Pfaffian of this matrix, which is just analog of determinant for skew-symmetric matrices, is correctly defined. Now I will not recall what is Pfaffian. A relation between Km invariant and the topological Z2 index, which I just introduced, is the following. This is the formula. This is the formula. If we exponentiate this equality, we obtain the equation relating the product of Pfaffians with topological Z2 index. So this is product of Pfaffians, and here is the topological index. If we set the determinant of Wx at fixed points equal to 1, then we get that Pfaffian at fixed points is just plus or minus 1. So the product in the left-hand side is equal to nu, and it will not change if we replace the Pfaffians by their signs. So we write this formula, which relates the K-Mill invariant with the topological index. So thank you very much.